All right, Robert, another accelerator that we want to talk about is AMX. This is a new one,
Yeah.
right, for us, AMX, but it's an old one, but a new one. Explain this to me.
Well, in many ways, it's an old play that we've been making to make sure that we are looking at workloads and looking at how can we accelerate them, how can we make the performance hit to the core less and less, but get you greater value and performance out of what you're investing in, which is the infrastructure here. AMX follows a long line of things that we have been doing for matrix math in HPC, right? Moving along the path to AVX 512 and the AVX steps that
Okay, so
started
this is in
before
the
it.
AVX family then,
It follows
AMX.
on from there in terms of other ways that we can apply math acceleration to math. And in this case, the AVX 512 gets us into what we've done with Deep Learning Boost, Intel VNNI for vector neuromorphic math, new instructions. In this case with AMX, it's the first time that we're actually putting a discrete piece of silicon in there that is the built-in accelerator to do advanced matrix math extension, but acceleration, right? So we're taking some of that math that you need to run in your code, and we're tuning it so it can actually run on the built-in accelerator, get maximum performance out of just doing that math really, really well. And again, leaving the rest of Xeon and its cores available to do other parts of the workloads that you need.
So this is a double win. When I heard about this, I was like, this is a total double win, right? Because I'm freeing up my cores to do what they need to do.
Yeah.
And I'm running faster because it's a built-in ASIC, for no better word, that does matrix math super fast.
Correct.
So this is a double win.
And I'll give you the triple win. You can run workloads like AI at a very high performance accelerated fashion without having to cross another chasm, which is bringing in additional compute hardware like a dedicated ASIC for GPU. That, or a GPU that you're having to add in. A lot of different designs. All of this still within the common form factor of what you normally expect out of a Xeon processor-based system.
So lower power, lower cost, lower OpEx,
higher performance, lower
higher
complexity.
Oh, awesome! This is great.
But now, how do we do it? We still need to go be looking after what are those workloads where the AMX actually is going to pay off.
Right.
How do I work with my vendors or my open source, my PyTorch, et cetera, that I can actually pull down the versions that I can actually use that have already been built in with the ability to accelerate that type of math using Intel AMX in a 4th or 5th generation Xeon processor or beyond.
Okay, so you brought up PyTorch, so I'm going to bring up large language models. Can they take advantage of AMX?
Absolutely.
So I don't need a GPU to run my large language models. I can run them on a Xeon processor.
You can. Now, the important part is you have options. You have options for good reasons that you need to consider. You need to consider how large is my large language model I'm trying to run? How small is it? There are still going to be limitations as to what you can fit into Xeon comfortably versus needing discrete, dedicated other cards, accelerators on board to run a very large language model. But as you look at those parameters, as you look at what you're trying to accomplish, we can make really good informed advice, education, prove it out, pilot it, and then take it to deployment. That's the type of thing that we need to be able to engage our customers with.